marked up the price by 50%. The price was later reduced by 10%, and finally the price was reduced an additional 20%. And the code was sold for $108 at a closeout sale. Find the original price in dollars paid for the code by the shop owner. All right, so basically the shop owner buys the code for some amount of money, and then it goes through a bunch of stuff, and then it's sold for $108. So we can set up an equation for this. So if we let X be the initial price of the code, we see that the price is first marked up by 50%. So what that means is we're multiplying 1.5 by X, because like when you're increasing by percentage, you are multiplying whatever number you're increasing by 1 plus that percentage. So we have this so far, but then this price was later reduced by 10%. So if we're reducing this by 10%, we're multiplying it by 1 minus 10%, which is just 0.9. And then this was again reduced by an additional 20%. So we're going to multiply it by 1 minus 20%, which is 0.8. And then finally, this is going to equal $108 because it was sold for $108. So now we can just solve for X, which is what we want. So X is going to equal $108 divided by 0.8 times 0.9 times 1.5. All right, so now what do we do here? Well, what we could do is make all of these into fractions and then try to simplify this big fraction. So when we convert them into fractions, this is just like 8/10, right? So we can express that as 8 over 10. So this can be 9 over 10. And 1.5 is just 3 halves. And then because these fractions are at the bottom, we can move them to the top if we flip them over. So then we have 10/8 times 10/9 times 2/3 times $108. And this is what X equals. And now we just need to simplify this. So we can take out a 9 from 108. Because 108 is just 9 times 12, right? Because 99 is 9 times 11, and 108 is 9 plus 99. So that means once we cancel out a 9 from here, that gives us 12. And then we can cancel out a 3 from 12 to get 4 here. And then, we can cancel out a 2 from the 8 and 10 to get 5 over 4. And then this 4, we can cancel out these 4s. So what do we have left? We just have the top 5, 10, and 2. 5 times 10 times 2 is just $100. So then X is going to equal $100. Anything you want to say, Bill?
Okay, so in this instance, the bottom is you can totally just multiply the bottom together, because 0.8 times 1.5, it'll end up being, that's 0.2, no, 2.4, no, sorry. It'll end up being 1.2, and 1.2 times 0.9, and 1.2 and 9, that's 1, 2, and 9. If you know 108 is 9 times 12, and if you notice that, you can just, the top divided by bottom, you can get 100 that way.
Yeah. All right, let's move on to number 4. All 3-digit numbers that have only the digits 1, 3, 5, or 7 in each position are recorded on slips of paper and placed in a container. If a slip of paper is picked at random from the container, what is the probability expressed as a fraction that it contains the number 111? All right, so we have a container and it's got a bunch of slips of paper. And each of the slips of paper has a 3-digit number on it, but all those 3-digit numbers have to have 1, 3, 5, or 7 as its digits. And all 3-digit numbers that have those digits are in the container. And we want to know what is the probability that we draw out 111. So this probability is going to be the number of 111s we have in the container over the total number of slips that we have in the container, right? So it's like our probability is number of 111s that we have over the total number of slips that we have. Now, there's only going to be 111 in there, right? Because it's only it only has each 3-digit number once. So this is obviously 1. So we just need to find the total number of slips that are in the container. So to find the total number of slips that are in the container, that's just the same as the total number of 3-digit numbers that have only the digits 1, 3, 5, or 7. So we just need to figure that out. So we can make a thing like this that denotes the place values of the numbers. And we can think about like the probabilities of each of these digits, right? So each of these digits come from the set 1, 3, 5, or 7. And other than that, they don't affect each other at all, right? So that means each digit will have 4 different possibilities. They can choose each of these numbers, and that's 4 different possibilities. And they don't affect each other in any way. So that means each of these digits will have 4 possibilities. That means to find the total number of possibilities that they make up with the total 3-digit number thing, we just multiply all their possibilities together. So that would equal 64. So because we have 64 possibilities for these 3-digit numbers, and all of them are in the container, and they are not repeated, that means the total number of slips that we have will be 64. So then our probability is just 1 over 64. Anything you want to say, Bill?
Yeah, no, this is fairly simple, so there's nothing really to know about this problem.
All right. Let's move on to number 5. What is the smallest positive fraction that when multiplied by 11/60ths results in a perfect integer cube greater than 1? All right, interesting. So we're looking for a positive fraction, the smallest positive fraction, and it's going to be multiplied by 11/60ths. Let's say the positive fraction is x. And it's going to result in a perfect integer cube that is greater than 1. So basically, integer cubes that are not 1, right? And what are the cubes? Well, the cubes are just like 1, 8, 27, 64, and so on. So for this problem, I don't really see a good way to do it, except for like testing each of the cubes. What do you think, Bill?
For this, so we'll multiply by. Right.
I mean,
Hang on, go. You go first.
it's just like we just use the smallest cube, right? Because like
Right.
x is just a fraction, so we want to make this side as small as possible.
Yes. Yeah. Greater than 1, so we'll use 8.
Yeah. Okay. So it's like this. So let's say our perfect integer cube is y, right? And we are trying to minimize x while keeping x a positive fraction. Well, the positive bit doesn't matter because it's obviously going to be positive. And yeah, so if we're trying to minimize it, and this is a constant, we're just trying to minimize y as well, right? And we just need x to be a fraction. So we're minimizing y as well. So if we're minimizing y, then 8 is our best number because it's our smallest perfect integer cube that is greater than 1. So we set y equal to 8, and then we just solve for x like that. So x is going to equal, so we're going to basically multiply both sides by 60/11ths so that these fractions cancel, and then on the right side we're just going to have 8 times 60 over 11, which is just going to be 480 over 11. So this is a fraction. It's going to satisfy the x being a fraction part, and we know this has to be our answer because this was our lowest possible y that we could have. And yeah, our answer is 480 over 11. All right, let's move on to number 6. So, okay, we've got a thing here. Given a set of numbers A, B, C, D, and the operation defined as follows, and we have a table here. we want to know what is the value of all of this. All right, so basically we just follow the table for the operation thing. So, and we have to follow order of operations here, right? So we have to do the ones that are most inside the parentheses first. So the one that is most inside the parentheses is I'll just call this triangle, a triangle D. So using the table, we can see a triangle D is going to be D. So this is going to equal D. And then we can replace D with that in our thing. So then we'll have B triangle D, triangle B triangle C. So this is all we need to find. Now B triangle D, we just use the table. B triangle D is C. And then triangle B triangle C, that's just A. Now C triangle A, use the table, that's just C. Yeah, our answer is C. I mean, that should be pretty simple. It's just using operation table. Okay, the harmonic mean of two numbers is the reciprocal of the average. Oh, sorry. The harmonic mean of two numbers is the reciprocal of the average of their reciprocals. Okay, it's just defining the harmonic mean. So express the harmonic mean of 5 and 7 as a mixed number. Okay, so they gave us the definition of harmonic mean in case we didn't know it. And then they just want us to like do that operation with 5 and 7. So let's look at their definition there. So the harmonic mean of two numbers, let's say they are x and y, is the reciprocal of the average of their reciprocals. So the average of their reciprocals would be 1 over x plus 1 over y over 2. And then this is a fraction, right? And it's in the denominator of this fraction. So we can bring it to the, or like we're just if we have 1 over a fraction, we're just like flipping the fraction to its reciprocal. So this is just going to equal 2 over 1 over x plus 1 over y. And so yeah, this is what harmonic mean is. Harmonic mean shows up pretty often, so this should probably be memorized. But harmonic mean is just not with two numbers. It can be with any number, set of numbers. So like if we have let's say we have a1, a2, all the way to a sub n. The harmonic mean of all of these numbers would be n over 1 over a1 plus 1 over a2 plus dot 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 plus so on, or 1 over an. And then so in the case where we just have 2, that's just 2 over 1 over x plus 1 over y. So yeah, so this problem tells us that tells us what harmonic mean is, but we should try to memorize harmonic mean in case we see problems that they don't tell us what it is.
Austin?
Yeah.
Buttercream is asking, in what type of problems are harmonic means used?
Oh, okay. Well, so I mean, with math counts, the problems are probably going to be pretty direct with what you're doing. So like, I don't know, like if harmonic mean comes up in math counts, it's probably going to be like somehow directly stated, like find the harmonic mean of stuff. But like as a general problem solving tool, I don't see harmonic mean coming up too often. Right, Bill?
Harmonic mean, it's not going to be something you use an awfully lot, that much. At almost never you'll have to use harmonic mean for something. In this
Like
case,
almost never. Like if the problem doesn't state harmonic mean in some way, it's very unlikely you'll have to like use harmonic mean on your own, if that makes sense.
in this case, they're just using harmonic mean as the way of testing whether you know how to understand like written written instructions, I guess.
Yeah. So I hope that makes sense. If it doesn't, just okay, yeah. Um Oh, okay, yeah. So we do have to find the harmonic mean of 5 and 7. So we can just plug in our function there. So it's just going to be 2 over 1/5 plus 1/7. So we're adding 1/5 and 1/7. We have to put them in a common denominator. So 35 is the least common multiple of 5 and 7. So to get 5 to 35, we multiply by 7 on top and bottom. And to get 7, oops. And to get 7 to 35, we multiply 5 on top and bottom. So we have 7/35 plus 5/35. That's 12/35. And remember, we had 2 over 12/35. So we have a fraction on the denominator. We can move it up to the numerator if we flip it. So then we have 2 times 35 over 12. We can cancel out the 2 with 12 to get 6. And then we just have 35 sixths. But remember, it asks for it being a mixed number. So we need to convert this into a mixed number. That's just going to be 5 and 5/6. All right, anything you want to add, Bill?
No, just yeah. This is a fairly straightforward problem. Just do the math and get the answer.
Yeah. All right, number 8. Find the sum of the first 21 terms of the series 3 plus 13 plus 23 plus ... So this is an arithmetic sequence, right? We have plus 10 between each of the terms. So if we're finding the sum of an arithmetic sequence, we can just use the arithmetic series sum formula, which would be the number of terms that we're adding times the median or mean of the sequence. Why is it median or mean? It's because the median and mean are equal for an arithmetic sequence. So it directly tells us the number of terms that we have, which is 21, and then we need to find the median or mean. So how we can do this is if we find the last number of our sequence, let's just call it x, I don't know, then our median slash mean will be the average of our last number x and our first number 3. So it'll be like that. And then, so now we just need to figure out what this last number is, right? So, the nth number in our sequence is going to be n minus 1 times our common difference, which is 10 plus 3. So why is it like this? Well, if you think of our first term, n will equal 1, right? So then this doesn't do anything, and we just have our initial term, 3. And then, once we go on to n equals 2, then this goes up by 1, so then we have 10 times 1. So we add one thing of our common difference to our initial term. So, and then as you increase n, it will keep on adding one more 10 to each of that. So, yeah, this is the formula for the nth term of our sequence, and and this is the 21th term of our sequence, right? Because we have 21 terms. So then if we plug in n equals 21, then we just have 20 times 10 plus 3. So that's just 203. So now we can plug in x equals 203 to our sum formula. So that's going to be 21 times 203 plus 3 is 206 over 2. We can cancel out 2 and 206. That's 103 times 21. Now, this is just going to equal 21 and 3 times 21 here, which would be 63. So 2163. Anything you want to say, Bill?
No, this is also a fairly straightforward problem.
Yeah, there's right. Okay, moving on to number 9. So for n, we have root 5n plus 4 equals 13. So we can just square both sides to get rid of the radical. The square of 13 is 169, and you should, for Mathcounts, you should probably memorize all of your integer squares up to 20. So it helps do your arithmetic faster. But yeah, so now we can subtract 4 on both sides. So we get 165 on this side, and now we just need to divide by 5, and that'll give us 33. which is our answer. That should be a pretty straightforward problem. The two legs of a right. Buttercream is asking, why is the mean equal to median? Is it only for an arithmetic series? So yeah, only for an arithmetic sequence will the median and the mean be the same, and it's just like a it's like a property of an arithmetic sequence. We could derive it, but like if you just generally remember it as a property, like you should be fine. And it's right. It's only with arithmetic sequences. Do you have anything to say there, Bill?
Also, where Cream is asking, do we have to
What?
account for the negative in this problem?
Okay, yeah.
I think we're
So
talking about number 9, I think.
yeah. So you don't have to account for negatives on this problem. Why? Because we're not taking. So the problem occurs when we have a square and we are taking the radical to get rid of that square. But okay, so like it's like this. So if we have the radical of x equals y, and we're solving for x, and we're squaring both sides to solve for x to get rid of the radical, right? So then we get x equals y squared. This is no problem. So there's no problem in this. Why? Because our initial radical here makes this radical x positive. So it has to be positive. So there's no sign problem here. But the problem occurs when we have like x squared equals y, and then we are taking the radical on both sides to get rid of the square. So why does this occur? Well, because in our initial equation, x squared equals y, x, I don't know, let's just say y is a positive number. X can be either positive or negative, and the square of it doesn't care what the sign is, it makes it positive, right? So then x could be positive or negative, and then when you radical both sides, then it looks like x is just a positive number when it isn't. It could be positive or negative, right? But there is no problem when you have a radical and you square to get rid of it. So the problem is when you have a square and you radical to get rid of it. I hope that makes sense. So here we just have a radical and we square to get rid of it. So we should have no problem here. And n. Oh, do we assume it's not imaginary? Do you mean like n is not imaginary? I mean like n oh, do we
Well, so if you have the square root of that equals 13, and
yeah, so it equals 13, right? 13 is not imaginary, so we don't have to account like the stuff under the radical being negative, if that's what you're asking. Yeah, no, it's fine. Okay, so yeah, but that is a very important that is a very important thing that comes up a lot. So basically, like again, if you have radical and you square to get rid of it, there's no problem there. But if you have a square and you radical to get rid of it, you have to account for the cases where the thing under the square is negative or positive.
and just something to note here, Mathcounts, it's highly unlikely that Mathcounts would expect you to know about imaginary numbers. Mathcounts is not at a level where it's going to expect you to work with imaginary numbers. So
I I mean I think they may show up. I'm not sure, but like in this problem, I mean like you don't have to account for imaginary numbers because it just equals 13. So yeah, no problem. Okay, so let's move on to number 10. The two legs of a right triangle have lengths that are in a 5 to 12 ratio. If the perimeter of the triangle is 105, express the length of its hypotenuse as a decimal number. Okay, so we have a right triangle, and we have its lengths or its leg lengths being in a 5:12 ratio. So to express that 5:12 ratio, we can just say we have 5 times x here and 12 times x here. So why can we do it like that? Well, if we take the ratio 5x to 12x, then that's just the ratio of 5 to 12, right? And so this is a Pythagorean triple, right? 5, 12, 13 is a Pythagorean triple. And because we have 5x and 12x here, that means this hypotenuse has to be 13x. And again, if you don't have your Pythagorean triples memorized, you could just use the Pythagorean theorem and you will get 13x here. So once we get this, we can just use this to find an equation for the perimeter of the triangle, which will be all of these sides added together, and it tells us that it's 105. So then we just do the algebra here. That's going to be 30x equals 105. So then we have x equals 105 over 30. So we can cancel out a 5 on top of bottom. So 105 divided by 5 is 21, and 30 divided by 5 is 6. And then we could cancel out a 3 from top and bottom to get 7 halves. And it wants it as a decimal number. Okay, it wants the hypotenuse. I got scared for a second. It wants the hypotenuse as a decimal number. So we can solve for x as 3.5, and then it wants the decimal. It wants the hypotenuse. So we multiply 13 by 3.5 and just doing a multiplication, we have this stuff, and we have 1 decimal here, so we're going to have a decimal here. So our answer is 45.5. Anything you want to say, Bill?
Right. So you will want to know the basic Pythagorean triple.
Yeah, we said that in our last
yeah,
meeting, right?
After that, if you can see the Pythagorean triple, which you should pretty much immediately see it, it should be fairly simple and straightforward.
Yeah. If you want a list of common Pythagorean triples, I think we listed that in our last video. So yeah. Okay, let's just move on to number 11. I'll just use this space. So the last year that was a perfect square was 1936. Find the absolute value of the difference between the next 2 years that will be perfect squares. Okay, so we just want to find the next 2 years that are perfect squares, and then we take the difference of them and have that be positive, right? So we want to find what 1936 is the square of. So that then we can just increase that whatever thing by 1. Like what I'm saying is, if we represent 1936 as x squared, we want to find what x is, and then we just need to find x plus 1 squared and x plus 2 squared, right? Because that will be the next 2 perfect squares. So how do we do this? Well, you could just estimate some squares and think about where you need to go, right? So if we estimate, I don't know, x to be, I don't know, let's just start with 50. Okay, so that will be 2,500, and that's too big. So let's move down to 40. So okay, why I'm squaring 50 and 40 is because they're nice tens numbers. So squaring them doesn't take much effort. Okay, so 40 squared is 1,600, and 50 squared is 2,500. So this is fairly in the middle. We can also use a trick here, and that's to look at the last digit of the square that we have, right? So okay, so how do I explain this?
So if the number
okay, let's look at this. So let's say we have b, which is a perfect square, and a, which is a any integer, okay? And then the units digit of a squared will be the units digit of b. And if the units digit of a squared is greater than 10, then you just whatever it is modulus 10, so you get rid of the tens part, will be the units digit of b, if that makes sense. So like if the units digit of a, so let me say that a with an apostrophe here, so a prime, let's say that's the units digit of a, so the b prime is also the units digit of b. So if a prime equals 1, then b prime has to equal 1 as well, because 1 squared is 1. And then, if a equals 2, then b prime has to equal 4. And then I'm just going to make a table. So if it's 3, then it has to be 9. If it's 4, it's 16, but we take out the 10, so it has to be 6. If a prime is 5, then b prime has to be 5, because 5 squared is 25, and we get rid of the tens. So 6 is 6, 7 is 9, 8 is 4, and 9 is 1, and 0 is just 0. Okay, so why is this the case? Well, like if you think about it, the units digit of a squared is only going to be affected by the units digit of a, right? Like the tens digit can't, like when you multiply it out, the tens digit can't affect the units digit at all, right? So that's where we're getting this from. Hopefully that makes sense. So basically, how we can apply this is we look at the last digit of the perfect square, which is 6, and that's like on our b prime side, right? So we only have 2 spots for 6, right? So that directly limits our a units digits to only 4 and only 6, right? So this limits our search by a lot. So it will definitely help you save time. And we already know, so this is telling us what the units digit of a has to be, right? And with roughly estimating stuff, we can easily find that the tens digit of a has to be 4 and then some units digit, right? So now we only have to test 2 squares, 44 and 46. Well, we only have to test 1, because if it's not 1, then it's the other. So, we could just test 44 squared. So that would be 176 here and 176 here. And then this is just 6391. So then we get 1936. So yeah, 1936 is 44 squared. Hopefully that makes sense. If it doesn't, just ask us. Anything you want to say there, Bill?
Wait.
I know we haven't finished the problem.
Okay, I was about to say, you didn't finish the problem.
Yeah. But like anything you want to say here. I mean, okay, so
yeah, that's no.
This is not just with squares, right? It's with any like power. Like if you raise anything to a power of anything, or like if you raise an integer to an integer power, then you can apply this units digit thing again, right? Because like when you take it to the power, its units digit at the end will only be affected by its units digit at the beginning. So then you can like make another table and then see which units digit go to which, and then that limits your search. All right, so now that we figured out x equals 44, we just need to figure out what 45 squared and 46 squared is. And then we take the absolute value of the difference between them. So 45 squared, I mean, we could just multiply that out. That will give us 225 there, and then that will give us 180 there, and then we just have 2025. And then 46 squared, we just multiply them together, so then we get 276 and 184. Then we add them to get 2116, I'm pretty sure. So then we just need to take the absolute value of the difference. So what they mean with the absolute value is just to make sure that you get a positive answer. And I hope everyone knows subtraction, and then we just get 91. Okay. So anything you want to say,
Yes.
Bill?
I was about to mention, and like Buttercream says, we can use the difference of squares for this
Oh yeah,
to do
yeah.
the
We can use the difference of squares, and that will be faster.
and yeah, it's not because the absolute value sign. You can still use difference of squares and then just absolute value the your final answer.
Yeah, yeah. So it's looking like it's looking for the absolute value of like 46 squared minus 45 squared, or like
The other way.
if you did it the other way, right? Okay, so like in
But if
this
you use
way,
difference of squared, you'll still get just positive
okay, yeah,
exponents.
yeah. But what I'm saying is like if you look at it here, we know that this is going to be positive, right? 46 is larger than 45. So we don't even need to worry about the absolute value if we're doing it like this. And if we're doing it like that, then we just like switch it around to get that. And then the absolute value goes away, and then you can do whatever you want. But like even if the absolute value were there, you could first apply the difference of squares and then get something and then absolute value. Yep. So let's move on to number 12. What is the greatest prime factor of the least common multiple of 21, 24, and 60? All right, so basically, we're finding the least common multiple of that, and let's just call it x. And then of x, we're finding the greatest prime factor. So if we prime factorize x, whatever the greatest prime that it has, that will be our answer. Okay, so an x is the least common multiple of 21, 24, and 60. And we've went over this like multiple times in our previous videos already, which is if we're finding the least common multiple of a set of numbers, we want to first prime factorize those numbers. So 21 is 3 times 7. This is actually cute. 24 is 2 cubed 8 times 3. And then 60 is 12 times 5. So 2 squared times 3 times 5. And then when you're finding the least common multiple, okay, this is a 3, by the way. Sorry if that's unclear. When you're finding the least common multiple of these, you want to take the greatest power of the primes for each prime that you see here. So like we start with 2, and we want to find which one has the greatest power of 2, and we take that power of 2. So we see that the largest power of 2 we have here is 2 cubed. So our least common multiple has to have 2 cubed, and that will be its 2 part. And our highest power of 3 is just 3, and our highest power of 5 is just 5. Our highest power of 7 is just 7. And then we have no other primes. So this is going to be the prime factorization of our least common multiple, and we just want to find the greatest prime factor of it, which is just 7. And you can do this slightly faster if you just know that the least common multiple, the greatest prime factor that it has, will be the greatest prime factor that any of its stuff before finding it has. Yeah. So then you just see like, oh, 7 is the biggest here, so we just use 7.
Yeah, so in this case, you don't have to actually go out and physically find the greatest common multiple, the least common multiple, if you know that each factor of each of the elements will be a factor in the least common multiple, you can just find the greatest prime factor in any of the elements.
Yeah. All right, let's move on. The diameter of a circle is increased by 25%. So the nearest percent, what is the percent increase in the area? Oh, okay. So yeah, this is a like percent increase thing. So we also went over this in our previous videos also. So we're getting a lot of recurring topics. But like it's if you increase, so okay, let's say we have a two-dimensional object. Let's say we have a square, and its side length is x, and its area is what do I denote as the area? Let's just say its area is y. If we increase x by some constant, or if we multiply x by some constant, y, oh, not equal, sorry. Then, okay, so it's like this. If we have x and we increase it, I mean, not increase, if we multiply it by some constant k so that it goes into kx, then y will have to be multiplied by k squared in this new thing that we have. So in this new thing, if our new side length is kx, then our new area must be k squared y. And why this occurs is because x is a one-dimensional thing and y is a two-dimensional thing. So if we multiply x by any constant, y must be multiplied by that constant squared. So here, and like if we have like a three-dimensional thing, like if y was a three-dimensional thing, like let's say we had a cube and the side length with that was x and y was the volume, then y would have to be multiplied by k cubed because it's a three-dimensional value. So we have the diameter of a circle, let's call it d, and let's call the area just a, capital A. So the diameter of the circle is increased by 25%. So again, what that means is it's multiplied by 1 plus 25%, which is 1.25. And we want to find to the nearest percent what is the percent increase of the area. So again, applying what we did here, d is a one-dimensional value. So if we multiply it by some constant k, then we are in this new thing. Our area, which is a two-dimensional thing, will be multiplied by that constant square. And then, so let's just square out this 1.25. So then we'll get 625 to maybe I should just okay, wait. So yeah, and then 521. Oh, okay, my pen is being really bad right now. Okay, so if we multiply 1.25 out, we get 1.5625. So our new area, if we increase, if we multiply 1.25 by d, then our area will be multiplied by 1.5625. And percent increase is like 1 plus the percent, right? So if we subtract this, thing by 1, then we will get what our percent increase is, right? So our percent increase will just be 0.5625. Convert that into percent by multiplying it by 100. So that would be 56.25%. But we want to round it to the nearest percent, right? So that's just 56% increase. Anything you want to say, Bill?
Right. So what Austin is saying here is that if you have if you're scaling by something, if you're scaling it by a proportion, then the area will increase by that proportion squared, and then the volume will be that proportion cubed, basically. And any aspect of it, if it's in like the fourth dimension, will be that the fourth, and so on and so forth.
Yep. All right, number 14. So for x, we have a big equation there. So I'll just write the starting equation all the way out. So we have 4 times 3 times n minus 1 plus 5 times n minus 1 minus 7 times n minus 1 equals x times n minus 1. Okay, so n minus 1 shows up a lot here, so and it's kind of messy to write out. So I'm just going to say y equals n minus 1. So because I'm lazy, I don't want to write out n minus 1 all the time. So okay, so what we can do here first is multiply the 4 by the 3, right? So then we'll just have 12y plus 5y minus 7y equals x times y. And we're solving for x. Well, all of our terms are being multiplied by y, right? So we can just cancel out all of the y's in our terms. So then we just have, okay, well, actually we can't exactly do that. We have to say y can't be equal to 0, right? Because it's like we're dividing this equation by y to cancel out all the y's, but we can't divide it by y if y equals 0, right? So we say y does not equal 0 if that affects anything then. So then we just have 12 plus 5 minus 7 equals x, so that's just 10 equals x. So we should check if y, we should check that y does not equal 0, which means that n minus 1 does not equal 0, but it doesn't say anything about it. So I don't know. We just assume that it doesn't equal 0. So then we just have 10 equals x. So our answer is 10.
Right. So in this problem, in the number 4 case, the problem should have stated that n does not equal n does not equal 1, but it doesn't. But in this case, if n was to equal 1, x can be any real number, which doesn't make sense. So it will be safe to assume that n does not equal 1.
Yeah. Okay, number 15, if one of the elements of the set, and then we have a bunch of stuff there, is chosen at random, what is the probability? Expressed as a fraction that its value will be 1. Okay, so basically we have some stuff here, right? We have some stuff, so like it's some stuff, and then comma some stuff, comma some stuff, comma some stuff, and then comma some stuff. And we're choosing one of these, and we want to find the probability that its value is 1. So we want to find how many ones that we have, right? And then if we just find the number of ones that we have, we just need to do it over 5 because that's the total number of stuff that we have, and that will be our probability. So basically, we had to find what all of this mess is for each of them. So we first have 60 minus 2 times 8, which is just 0. 2 times 8 is 16. And then 3 squared is 9, times 2 is 18, minus 17. Oh, look, we have a 1. So this is a 1 right here, this is 0. And then this is 2 times 4 is 8, plus 6 is 14, minus 13 is 1. We have another 1. And then 8 over 3 is, 24 over 3 is 8. And then 8 times 8 is 64. That's very big. And then 3 squared is 9, times 4 is 36, minus 35 is 1. So we have 3 ones, we have 5 numbers, so our probability would be 3/5. So this is a question just to like, I don't know, like it's like just some algebra stuff. Anything you want to say there, Bill?
Yeah, no. So that problem may seem kind of intimidating at first, but once you read the problem and find out what it's really asking for, it's fairly simple.
Yep. Number 16, all bags of colored candies in a certain store are mixed so that the colors are in the same proportion in all of the bags. One bag was examined and a count of the different colors was summarized. And we have that. If you bought 2 bags, each containing 1,000 of these candies, how many yellow ones would you expect to get? Okay, so the first thing that we was saying, like all bags of blah, blah, blah are mixed so that the colors are in the same proportion in all bags. That just means like the ratio that we have here can be applied to like ratio of anything with the bags that we have, right? So it's saying if we bought 2 bags that each have 1,000 candies, which would be 2 times 1,000, that would mean we have 2,000 candies in total, right? We want to figure out how many yellow ones we would expect to get. So we should find the ratio of, we should find this ratio right here of yellow to the total number of candies, and then we can just apply it to here. So we should look at the tally marks. So we have 7 red, we have 9 brown, we have 3 orange, we have 8 green, we have 13 yellow. And we need to add all of these up to find the proportion. So 7 and 3 is going to be 10, and then 3, 8, and 9 is going to be 20. So that's just 30. So that's just 40. So we have 40 candies in total, and we have 13 yellow. So that means the ratio of yellow to total candies here is 13 yellow over 40 candies. I'll just label candies as C. And like what I said in the beginning, we can apply this ratio to anything, any candy stuff that we have. So if we want to find the yellows of 2,000 candies, we can multiply this by 2,000 candies, and we cancel out the candies. And then this will just give us some y. So then we can cancel out 40 with 2,000. So we can cancel out 0 first, and then cancel out 4 from 200 by dividing it. So that will be 50. And then 13 times 5 is 65, right? And then we have a 0, so that equals 650. So our answer will be 650 yellow candies. That should be pretty straightforward. In a school election, candidate A got 33 1/3% of the votes cast, B got 9/20 of the votes, and C got 2/15 of the votes. And the only other candidate, D, got remaining 75 votes. How many students voted in the election? So let me just list them out. So we have candidate A, B, C, and D. And so for candidates A through C, it gives us some proportion of the total votes cast. A is 33 1/3%, B is 9/20 of the total thing, and C is 2/15 of the total thing. But for D, we get an actual number, which is it got the remaining 75 votes. So how we can solve for the total number of votes is if we find the proportion that D got, then we could set up an equation to like equate the proportion times the total number of things equals 75 because we got an actual number here. And how we can find this proportion is, we can add up all of these proportions and then subtract it from 1, right? So like 1 is the total proportion, and these make up all the proportion except for D. So let's say K is the proportion for D of the total votes cast. That means K is going to equal 1 minus 33 1/3% minus 9/20 minus 2/15. Now, 33 1/3%. You can so we want to try to get it out of the percent and put it in a fraction. Fraction would be best here. You can do this in many ways. So one thing you can do is list out the 1/3, right? 1/3 is just 0.3333 and so on. And then to get rid of the percent, you just divide it by 100, right? So you move the decimal 2 places to the left, and then you have 0.333 and so on. That's just 1/3. You can do this in other ways as well. We have 33 1/3%. We can convert this into an improper fraction by multiplying 33 times 3 and then adding 1. So that would be 99 plus 1, that would be 100/3%. And then to get rid of the percent, we divide by 100. That will give us 1/3. So there are many ways. Just do one of these and you'll get 1/3. So then we get K equals 1 minus 1/3 minus 9/20 minus 2/15. Let me just do the 1 minus 1/3 first to get 2/3. And then now we have to solve this. It's kind of messy, but it should be fine. So we have to find a common denominator that we can put these into. And so that would be, so basically we're finding like the least common multiple of these, right? So, I mean, we just talked about it. So 20 is 2 squared, 5, and 15 is 3, 5, and 3 is just 3. So our least common multiple will have to be 2 squared times 3 times 5, which is what? Which is 20 times 3, 60. So that means we can just put these fractions into the denominator of 60, and then we can figure out what it is. So to convert 2/3 into 60, we multiply top and bottom by 20. So then we'll have 40/60 minus, and that'll be times 3 on top of bottom. That'll be 27/60. And then minus, we multiply it by 4 on top of bottom. So that'll be 8/60. And then this will just be 40 minus 27 minus 8/60. And that is just 13 minus 8, so 5/60. And then we can simplify this to 112. So now we finally get K, which was the proportion of total votes that candidate D got. So now let's say X is the total number of votes that we had. That means 1/12 times X will equal the number of votes that D got, which is 75. So X equals 12 times 75. And this is not too bad to multiply out, but you can actually do it, you can do it a little bit faster if you take out a 4 from the 12, and then know that 4 times 75 is 300. So that means we just have 3 times 300 is 900. So x will equal 900, and that is the correct answer. Anything you want to say, Bill? Bill? Uh-oh, is he dead? Okay, Bill says he's going to step out for a second. That's fine. So, but yeah, this problem is kind of long. But it's kind of just a lot of algebra stuff. All right, let's move on. If a typist produces 4 typed pages for every 5 handwritten pages, and can type 14 pages per hour, how many hours will it take for him to type 105 handwritten pages? Okay, sorry. If a typist produces 4 typed pages for every 5 handwritten pages and can type 14 pages per hour, how many hours will it take him to type 105 handwritten pages? Okay, this is I don't know. I feel like this problem is kind of weird, but it's saying let's call typed pages T and handwritten pages H. So it's saying the typist produces 4 typed pages for every 5 handwritten pages, and can type 14 pages per hour. And then it wants to know how many hours will it take for him to type 105 handwritten pages. So we have a proportion here, right? And that's 4t over 5h equals 1. And we want to find 105. We want to find the number of hours that will take him to type 105 handwritten pages. Okay, so this is 14 type pages per hour. So what we can do here, oh crap, okay, let me label hour as HR, not H, because we already labeled this as H. So that means we can multiply, or we can divide this by 14t per hour, and this will give us 105 over 14 hours times h over t. So why did I divide it? Well, this is to get the correct units so that we have hours on top and we have an h over t. And we want this h over t because we have like a proportion of h over t right here, right? So we can say if we take this stuff to the other side, we have t over h equals 5 over 4. And so that means h over t is just 4/5. So basically we can like substitute. So this is kind of weird using units like this kind of like as numbers, but like with proportion of units, you can kind of like treat them as if like they're numbers. So we can substitute this h over t equals 4/5 into here. So then we just have 105 over 14 times 4/5. Or with the unit of hours, this is what we want to find, right? Because it has a unit of hours, and we want to find a number of hours that will take him to type 105 handwritten pages. So now we can cancel out the 105 and 5, so that will be 21. And then we can cancel out 2 from 14 and 4, so that will be 7 and 2. So that will be, oh, okay, and we can cancel out a 7 from 21, so that will be 3 and 2. So that will give us 6 hours, which is the correct answer. So I hope that makes sense. Yeah, with units, you can do stuff like that. Like with the proportion of units, you could like substitute the proportion of units in. If you don't want to do it like this, you can also do it like the kind of conventional way with finding I don't know, like doing some more proportion stuff. If you want to ask questions about it, you can just ask about it in the chat. Yeah, is Bill still here? Okay, I think he'll message me when he gets back. Okay, let's do number 19. If the values of x shown below are substituted into a quadratic formula, the corresponding y values are determined. And we are given a table with some x values and some y values. If the same formula is used, what will be the value of y when x equals 14? So we have some quadratic formula, right? We have like x squared plus x plus, okay, I'm sorry. It's like, we have, okay, let me just undo all this. We have some quadratic formula. It's like ax squared plus bx plus c, and it equals y. Quadratic relationship. And basically, we want to find what this formula is so that we can plug in x equals 14 so that we get something for y. Now, one way we can do this is to like plug in values of x, and we get multiple equations for a, b, and c. And then once we have 3 equations for them, we can just solve them by system of equations. So like, let's first plug in x equals 2. So that will give us 4a plus 2b plus c equals the y value for that 7. So it equals 7. And then let's plug in 3. So that will be 9a plus 3b plus c equals 17. And then we have 16a plus 4b plus c equals 31. So now we can solve this as a system of equations. We can solve for a, b, and c, and then we can use, then we would have solved for the formula, and then we can plug in x to get y. So let's go ahead and do that. So how should we do this? Well, we can take this equation, take this third equation, and subtract it from the second, or subtract it by the second, so that we get 16a minus 9a, which would be 7a, 4b minus 3b, which is just b, and c, the c's cancel. Like why I subtracted it was so that the c's can cancel. So that would be 7a plus 7a plus b would equal 31 minus 17, and that would just be 14. And then we want to get another equation with a and b so that we can solve for a and b. So how we can do that is we could take this third equation and subtract it from the first equation instead, so that we still cancel out the c's, and we have a new equation for a and b. So that would be 12a plus 2b equals 31 minus 7, which is just 24. Okay, and we can divide this equation by 2 actually. So 6a plus b equals 12. And then now, we can just solve for b in here. So that b equals 12 minus 6a, and we can substitute b into right here. And then we can just solve for a. So then we get 7a plus 12 minus 6a equals 14. Then we have a plus 12 equals 14, so a equals 2. Now if equals 2, we can put a in here, and we get b equals 0. And then we can just use any of these equations to find what c is. So using our top equation, we have a plus 0 plus c equals 7, so c equals -1. So our equation will be 2x squared minus 1 equals y. Now that we have this equation, we can plug in x equals 14. Like I said before, you should probably want to memorize your integer squares up to 20. 14 squared is 196 times 2 minus 1 is going to equal our y. And 196 is just 200 minus 4, right? So 2 times it is just going to be 400 minus 8, which is just 392. I want to subtract 1, and then that will be just 391.
Okay.
Bill, are you back?
Yes, sorry, I have to do something. So in this case, if you look at this is like a lot of equations to solve. Another way you can do this is just finding the pattern in here. If you just look at the differences, the difference from 2 to 3 is 10 is 10. From 3 to 4 it is from 3 to 4 it's what? 14. From 4 to 5 it's 18. And so on and so forth. If you do that, find you can just like bash it all the way to 14, and that might be faster than finding it out the
Um,
equation way.
do you want to show that on your board?
Yeah, that's okay. Yeah, sure. So what we can do is so what we have 2 at what was 2 at 7, 2 was at 7, 3 was at 17, 4 was at 31, and 5 was at what? 5 was at 49. 5 was at 49. So if we take these, because how a quadratic works is that the amount is increasing at a fixed amount. So here it's plus 10, and here it's plus 14, here it's plus 18. And so from each one of these, the amount you're adding by it's going up by 4. And so, and then so if we have 6, 7, 8, 9, 10, so on and so forth. And then so from here to here, it will be added 22. Here to here, here to here, you'll be adding 26. Here to here, you'll be adding 20, 30 from 30. And then from 8 to 9, you will be adding 34. 9 to 10, you will be adding 38. And so we know that 10 is, we know from this that 10 is 199. So 10 is 199. And you 10 is 199. So if we 10 is 199, and then we added 38 to here. Sorry. And oh my goodness. We added 38 to here. So added 38. And then so from 10 to 11, we will be adding the amount we're adding by will go up by 4. So this will be 42. So we'll be adding 42 to this, which will be 241. Then likewise for 12, we will be adding 46. So 287. For 13, it will be adding 50. So that will be 337. And then for 14, we will be adding 54. And so that will come out to 391. And yeah, 391 is our answer in this case. So that's just another way to do it.
Yeah. Um, yeah. Because it gave you the 10 term here, doing that way isn't too bad. Um, Buttercream is asking, can we still go up by a constant amount, even though the quadratic can go down as well?
Well, so in that case, if the quadratic is let me show. So so if the quadratic is going down like this, when it's going down like this, on this side you're still adding by a constant amount. Like you're still the difference is still you're adding a constant amount to the difference. If it's like this, you're still you're still adding a constant amount. It's just that the constant amount here is negative. Do you get what I mean here? So when it's going down here, the difference is negative, but the difference is still going up. So it's becoming less and less negative, and then it becomes positive, and then here it's similar. Yes, it is still a constant even though it turns.
Yeah. Um, like I don't know, if you have like a curved down parabola, um, you're adding, so it's like so okay, when you have okay, think about an arithmetic sequence. An arithmetic sequence is like, let's say A1, A2, and so on. And you're adding some constant value. Let's just call that K. If we graph this, so to speak, we would get a graph of a line like this. And basically what this K is signifying is the slope of the line. So with a quadratic thing, this K is not constant, right? But the thing that is adding to it is constant. So if you think about that constant adding thing is that you're adding to the slope, right? So with like a curved down parabola, this slope, it's initially very negative and it's getting less negative, and then positive, very positive. You're getting the slope from negative to positive. You're adding it by some like constant amount, basically. Yeah, I don't know. I hope that makes sense. Um, is it still adding even though it's not like linear? What do you mean? Sorry. It's like if you took the slope at each of these points, it should be following the arithmetic sequence. So it would be adding by some constant term. Yeah, but my graph isn't totally good here because it kind of goes to infinity very quickly. I mean that's fine though. Like it can be like this could be like 0, this can be like 1, and this can be like 2. Well, if it was graphed properly. I'm talking about the slope. Sorry, is that what you're asking, or? So it's not that uh Bill, I think you're echoing.
Oh, sorry.
Yeah. It's not the term that is going up by a constant amount. It's the slope that's going up by a constant amount. You're correct in that if the terms were going up by a constant amount, it would just look like this, right? It's just a linear graph. But here, our slopes are increasing by a constant amount, which is definitely not the terms, right? And the slope means like how much the term is changing. So when we have greater slopes, so we're increasing the slope, that means our term is going to be increasing faster and faster because we have larger slopes. and that is why it increases faster than a normal linear line. Does that make more sense?
So what it's saying is that the the slope will be, even though the slope is constant. So if you're listing the slope out, say on a um on a graph, the slope, even though the slope will be like negative 5, what the slope will be, say -5, -2, and then 1, 4. It will still be increasing. The slope will be increasing at a constant, but the line will be curved.
Okay, so are you like confused about the turning point? So yeah, so the slope is still increasing at a constant every all the time, even when it's on the like a negative side, right? So like let's say we have some very negative slope here. Maybe it's -2. Okay, I know my graph isn't drawn very good. And then here it's -1, and then here it's 0, right? So it's still increasing by that constant amount. It's going from very negative, and it's adding, and you're going more positive. Does that make sense? And like your like Q points here, I don't even know. Like maybe this Q -2. This would be positive, even though the slope is very negative. I mean, if we're having it positive here, it doesn't have to be positive, right? Like if our origin was like here and our graph was like that, then it wouldn't be positive. No, well, like quadratic graphs are definitely related to arithmetic sequence graphs because like its slopes is an arithmetic sequence. That's how it's connected. That's how a quadratic graph is connected. But like a certain I don't know, a certain type of graph doesn't necessarily have to be connected to an arithmetic sequence, right? Like I don't know, like you could have the square root function, or actually, I mean that's just like the arithmetic sequence square rooted, but like I'm not sure what you're asking. Like the slope, like if this is the square root function, square root x, the slope of the square root x is definitely not an arithmetic sequence. That's just the property of quadratic graphs. Like if you have a graph and its slopes are an arithmetic sequence, then that graph has to be quadratic. And only quadratic graphs are like that. No, so linear. Okay, so that no, sorry, that's different, right? Linear graphs have a constant slope, right? So the slope is not changing. The slope is not like an increasing arithmetic sequence. Like in a linear graph, the points are the arithmetic sequence, but in a quadratic graph, the slopes are the arithmetic sequence. Okay, yeah. Um, and it doesn't have to be like a curved up parabola. It can also be a curved down parabola. And with a curved down parabola, that's saying the slope is starting positive, right? We have some positive slope, I don't know, let's say this is +2, like a slope of +2. And then here in our graph, it's becoming more and more negative, right? And this follows an arithmetic sequence. So, but like what would it increase by a constant amount? The slope increases by a constant amount, which is a negative, something negative, but the terms are not increasing by a constant amount. The terms follow something different. The terms follow a quadratic sequence. So, I mean, like what do you mean by it? The slope still does increase by a constant amount. But in the curved down parabola case, it's the constant amount is negative. Are you talking about this graph here? It seems that the slope decreases after increasing by a constant amount at the turning point. Okay, no, yeah. So this might be a little bit confusing, but like look at the slopes here. Just look at the slopes. We're going from +2, +1, then 0, -1, -2. Here, it's always subtracting by 1. The slope never decreases. I mean, sorry, the slope never increases. It's always decreasing. What you might be confused about is that while the slope is decreasing, the terms can still be increasing. Now, why is that? Well, because the terms increase just depending on when the slope is positive. But when the slopes are decreasing, that doesn't mean the terms have to decrease as well. If you're looking at the terms keep on increasing to here. Now, why is that? Well, because on this side, all the slopes are positive, and then on this side, all the slopes are negative. But the slopes still follow an arithmetic sequence. Does that make sense? Sorry, could you I don't know, could you clear up what you're confused about? Maybe we should look at a Desmos graph here. No, it's fine. Okay, hold on. So do you want us to look at a positive quadratic graph or a negative quadratic graph? Negative? Okay. Okay, so here's a standard negative quadratic graph, right? So let's just look at the slopes for a second. Okay, we're only looking at the slopes. We're not looking at the terms at all, right? And you get what slope is, right? Like the slope at any point would be like the line tangent to this graph right here. I can't really point with it well. Yeah, I can't really point with it. But if you think about it, like the slope at this point, this random point, would be if we took a line and we made a tangent to this point, so it's touching the graph just at that point, and whatever the slope of that line is whatever the instantaneous slope at that point. So whenever we talk about a slope at a point, we're talking about the instantaneous slope. That's something very crucial in calculus. But it's basically like if you zoom in on a curve, right? The curve becomes increasingly linear, and so whatever that slope is, that's the like instantaneous slope for the point. Like as you zoom in, like it actually becomes a line that is the slope, that is the instantaneous slope of that point. So like at this 0 point, the instantaneous slope would be 0, right? Because if we took a horizontal line, it would be tangent to this 0 point, and the horizontal line slope is 0, so the instantaneous slope at 0 is 0. And then if we look at 1, the slope right here is actually -1. The values and the slope actually matches up, but don't get confused on that. Like if you take a line right here at x equals 1 and just put it tangent to that point, it would have -1 slope. So the instantaneous slope at 1 would be -1. And then if we look at 2, the instantaneous slope at this point is -2. Like I can even graph it for you actually. Here, look. If we have y equals 0, that is tangent to this point right here. So that's how we know that the instantaneous slope at this point is 0. And then let's say we have -x. So this slope is, oh, actually, so, okay, I'm sorry. So the slope at, actually, okay, yeah. The slope at 1 is actually not -1. I was mistaken there. The slope at 1 is actually -2. So like, look, if I graph this -2 plus 1 line, it is tangent to the quadratic graph at x equals 1. So we know that, and the slope of this line is -2, right? So we know that the instantaneous slope at x equals 1 of this graph is -2. And if we graph this -4 plus, I don't know, 3? No, it's 4. This is tangent to our quadratic graph at x equals 2. So here, we know that at x equals 2, the instantaneous slope is -4 because the line slope is -4. And then we can keep on doing this to 3. 3 slope would be -6x plus, I don't know, 6 plus 8 plus 9. Now this is getting a little bit messy. Where is 3? 3 should be right here. And what is that? That's my block line. Okay, yeah, that is tangent. Okay, yeah, but so here at -3, I mean not -3, at 3, right here, 3 -9, that block line is tangent right here. To graph is, sorry, you can't really see it well anymore. But like at 3, our slope is -6. So now let's take a step back, right? What was our slope at 0? 0. What was our slope at 1? -2. What was our slope at 2? -4. What is our slope at 3? -6. So that follows an arithmetic sequence, right? 0, -2, -4, -6. That follows an arithmetic sequence. That's what we were saying. The slopes follow an arithmetic sequence. If we graph the slopes here, it would still be following an arithmetic sequence, right? So it'd be like 2x plus 1, 4x plus 4, and 6x plus 9. So here we can see that the it would be symmetrical like on the other side, right? So like the slope at -3 would be 6. The slope at -2 would be 4. And the slope at -1 would be 2. So that still follows the arithmetic sequence, right? At -3, we have 6. And then at -2, we have 4. So that's decreasing by 2. And then at 1, we have a slope of 2. And that's still decreasing by -2. I mean, it's still decreasing by 2. And then as we go to 0, we decrease by 2, and we get a slope of 0. And then we still decrease by 2, and then we get more and more negative slopes. Are you getting that now? So, oh yeah, no problem. So yeah, but it does get confusing with the terms, because like the terms don't exactly like I don't know, the terms can get confusing because it looks like it's weird and stuff. But if you just look at the slopes, then yes, it's an arithmetic sequence. And again, in our negative quadratic graph, our slopes are getting more negative. And in our, if we have a positive quadratic graph, then our slopes would be getting more positive. And so this ties into calculus pretty well, actually. So in calculus, what we can do in functions is we can take the derivative of a function. And that derivative function is a function for the slope of your original function. So if you take the derivative of -x squared, you get -2x. And the -2x function is the function for this instantaneous slope at any point x, right? And it follows what we said here, right? Like at x equals 1, if we plug it into -2x, then we get an instantaneous slope of -2, which is what we found. And because that derivative of -x squared is a linear function, that means its slopes follow a linear function, which like was what we were saying. It follows an arithmetic sequence, basically. And like, yeah, no problem. So, and a sequence is like if we just take individual points and they're separated by some like constant amount, right? Like a sequence could be like we take a point at x equals 0, we take a point at x equals 1, and we take a point at x equals 2. But like when you're working with functions, it's kind of like a infinite sequence, right? So then like the slope is increasing by a constant amount. I don't know. That's kind of okay. I think we're good now. But yeah, that goes on to more stuff. But you'll learn all of this in calculus. But I guess it's good to know for now. Anything you want to say, Bill?
Yeah, no, so yeah.
Okay. Let's move back to our thing. What problem were we on? Oh, okay, we're still on that problem. So yeah. So like, okay, let me explain this a little bit more actually. Maybe just to tie everything together, right? So the function that we got was 2x squared minus 1 equals y. And let me go back to this one. That works. So we can graph this function, right? Y equals 2x squared minus 1. So this is the graph for our arithmetic sequence. And if we look at like x equals 2, for instance, on our graph, at x equals 2, it equals 7, right? 2, 7. and that lines up with our sequence. And if we look at x equals 3, it's like right here, then you can see it. We have a point 3, comma 17. So this is another point of our sequence, right? So what we mean by this sequence being a quadratic sequence is that if you plot the sequence on like a graph or something, like if you plot the sequence, it follows the graph of a quadratic. It follows the graph of a quadratic formula, or of a quadratic function. So that's why it's a quadratic sequence. And so that's why it's like that's why the slopes are like increasing by a constant amount at every point and stuff. Okay, I don't know. I think we should probably move on now. Yeah, no, but if you have any other questions, just ask. Yeah, no problem. So now we have number 20. T is the tens digit and N is the units digit of all that, which is a 7-digit number. If all that is divisible by 99, what is N over T? Oh, interesting. Bill, what do you think about this problem? Oh, okay, so actually, so I can think of 2 ways to do this. It's to look at the divisibility by 9 and 11 of this, but we can also just like divide this by 9 until we get there and then like solve for it, right? Oh, what do you think, Bill?
Right. So, first of all, what you can notice is, well, first of all, you can find the possible pairings for T and N because because we know that all these digits added up have to be a multiple of 9, and alternating adding and subtracting each digit would have to equal 0. So
Yeah. So
yeah,
okay.
we can
So
find
what?
out some of the possibilities. The possibilities
Yeah. So like what we're doing here is let's just call the number x, and if it's divisible by 99, um, I'm pretty sure this notation means it's divisible by 99, right? I don't know, right?
Yes.
Okay, yeah. If x is divisible by 99, x has to be divisible by 9 and divisible by 11, right? Because, 9 and 11 are just factors of 99. And why we put it like this is because the divisibility by 9 and 11 have rules with them. And then we could just use those rules on the number. Use those rules on the number, and we can get some like equations for n and t, and then we can like solve more about it. So the formula for 9, if something is divisible by 9, all of its digits has to add up to a multiple of 9. So let's go ahead and do that. So we have all of that, and then plus t plus n, and it has to equal, and this has to be divisible by 9. And so let's just take out like 9s. So we have 1 and 8, that's a 9, and 8 and 2, that would be 10, so then we just have 1. So now we know 1 plus t plus n has to be divisible by 9. And n and t are digits, right? So all of this, if they were at their max numbers, which would be 9 and 9, then this can just only equal what, 19? So that means this has to equal 9 or 18, right? Because this is always less than 19, and it's always greater than 1, or it's always less than or equal to 19, and it's also always greater than or equal to 1, but it also has to be divisible by 9. So that means 1 plus t plus n has to equal 9, or it equals 18. Okay, and then, so we have an or thing here, right? So we can't exactly figure out like what they are. So that's where we apply the 11 rule. So if something, man, everything is getting very cluttered. But I'll box this. If something is divisible by 11, the alternating, so like you want to add up the digits with alternating signs. So we can just start with 2. It doesn't matter what sign we start with 2 with, but like we start with 2 and then we minus 1 and then we plus 3 and then we minus 5 and then we plus 8 and then we minus t and then we plus n. This has to be a multiple of this has to be divisible by 11, or it has to be negative and divisible by 11. So like this can equal like negative 11 or negative 22, but it can also equal 11 or 22 or 0, right? So then let's just simplify this. So this is like 3, and then this is like 1, and then this is 7. So we know that 7 minus t plus n has to be some factor of 11, right? So I mean, I guess we can just look at its maximum and minimum. So to get this to its maximum, we have to have n equals 9 and t equals 0. So then its maximum is just 16. So max is 16, and then what's its minimum? Its minimum would be if t was 9 and n was 0. So its minimum is negative 2. So because of that, this has to equal 0 or 11. Okay, so now we have, and we are running out of space. Let's move all of our equations right here. So we have 1 plus t plus n equals 9. What do you think, Bill? Do you think this is a good way to do it?
Yeah, I think it's fine.
Oh, okay. And then we set it equals 0 to 1. And I mean now what do we do? Now we just we can just take any pair of these and then solve for it, right? And if it gives us t and n as not 0, I mean like not an acceptable digit, then we just take some other combination of equations, right? Like what do you think, Bill?
Right. So, yeah, it doesn't, as long as n over t ends up being a real number, I think that will be fine because it doesn't specify any limitations for n and t. So, as long as it
Yeah.
satisfies this condition.
Oh, why do we look at the maximum? So it was so that we can separate these into equations, right? Because like in reality, these can equal to 22. It can equal 33. It can equal any multiple of 11, right? But if we look at the maximum of it, then we can just like kill all of these equations, right? Because it can't ever be that big. So then we just have these few equations. Okay, so now let's just look at the first set and see if it works. So if we add them, we get 8 plus 2n equals 9, and then 2n equals 1. So that is now an acceptable digit. Let's look at this one and that one. Then we have 8 plus 2n equals 18, and then we get 2n equals 10, n equals 5, and there we get an acceptable digit. And then if we solve for t there, we get 12 minus t equals 0. Oh no, t is not an acceptable digit, right? T is 12, so that won't work. So now let's try this bottom one with this bottom one with that top one. If we add them, we have 8 plus 2n equals 11, but this is not going to work, right? Because we have 3, so that's going to be a fraction. And then now we just look at the bottom ones. So if we add them, we get 8 plus 2n equals, oh crap, I think I did something wrong. We get 8 plus 2n equals 29, which doesn't work either.
Well, N can be 0. Oh wait, never mind, I'm dumb. Ignore that. Yeah. So
Uh,
this way doesn't. So you could try considering another pair of functions. Maybe this pair of functions doesn't work out.
no, I think we consider all of them, right?
Um,
Okay, wait, let's check back. So if we do the first pair, we have 8 plus 2n equals 9. That does not work. If we look at the bottom pair, we have 8 plus 2n equals 19. No, 29, which does not work. And then we look here, that's 8 plus 2n equals 20, which n equals 12, right? So that does not work. No, n equals 6. Wait, what? Okay, wait. If we look at this one and this one, then we have 8 plus 2n equals 20. So then 2n equals 12. So then n equals 6. Wait, how did I not see this before? Okay, so if n equals 6, then we have 13 minus t equals 11. Oh my gosh, finally. So now we have t equals 2. So now we finally have a pair of digits, 6 and 2. N equals 6, t equals 2. And we want to find n over t. So 6 over 2, finally get 3 as our answer. All right. That's going to be it for today. I hope this meeting was helpful, and thanks for coming. If you don't have any more questions, you can just leave now.